This is going to be an explanation of how to solve a pithball hanging on a string kind of problem. This is similar, if you're working on my problem set, to problem 4 in the Coulomb's law problem set. So this will be similar but with different numbers. Suppose I've got a pithball and it has positive 4 nanocoulombs of charge on it, and I see that it's tied to a string and it's hanging at an angle of, oh, my favorite angle, 37 degrees from vertical like this. And I'd like to know what is the charge on this point charge pithball, Q, that is a distance, let's say, 6 centimeters away. So why is it important that these are point charges? Well, Coulomb's law only applies to point charges, so I'm going to assume each of those charges is located at its own center of charge. So let's see, how can we start this? Oh, I need to know something else as well. Let's say the mass of this pithball is 1/100 of a gram, 0.01 grams. So what's our first step here? Well, I need to know all the forces on that pithball. So I know it's being pushed away, so that tells us already what the charge of this guy is right here. What must that be? Well, if this one's positive, this one has to be positive too. So capital Q is a positive quantity, and I see that there's a repulsive electric force here. The electric force. That's an F. And what other forces are acting on this guy? Well, I remembered that I had to have mass on it. So I know, I'll use green because it's being pulled toward the Earth. This force of gravity is pulling this way. That's pretty simple to figure out. That's mg, and I need to use kilograms and meters and seconds when I calculate that force. And what's the third force? Well, the third force is the force of this string, the tension, which is pulling this direction right here. So now we just want to figure out what are those forces in each direction. I see that this thing is at rest, so the net force in the vertical direction and the net force in the horizontal direction must be, 0. So how do we go about doing that? Well, I see that this tension here, I can break this guy into two parts. One part that's only pulling this way. So if this guy's T, I'm breaking that into the adjacent side of this angle. I know if this is 37 degrees, I got a 37 right here too. So right up here, adjacent to that angle, I'm going to have a T cosine of 37 degrees. And over here, of course, T sine of 37 degrees. So what is the net force here? Well, I see that pulling to the right, I've got T sine of 37 degrees minus that electric force. And that is equal to 0. And then we also have T, the vertical part, cosine of 37 degrees minus that gravitational force, mg. That also equals 0. So what is that electric force? Well, we're going to use Coulomb's law here to figure that out. The electric force depends on the size of both charges and their distance from each other. So how do we go about that? Let's see. It is equal to the Coulomb constant, Ke, times the first charge times the second charge, divided by the distance between them. Remembering to use SI units. So Coulomb constant is 9 times 10 to the 9 units, Newton meters squared per Coulomb squared. And what is my first charge? 4 nanocoulombs, so that's 4 times 10 to the minus 9 coulombs times Q, the charge I don't know, and that's divided by the distance between these guys, squared. So what is that distance? It's 0.06 meters, 6 centimeters, and we got to square that. So you might be wondering, how did this guy pick these numbers? And you are about to see. I wanted this to work out nicely, so I've got 9 times 10 to the positive 9 times 9 times 10 to the negative 9. That is going to cancel and give me just 1, and 9 times 4 is 36. So we have 36Q over 0.06 squared. That's 6 times 10 to the minus 2 squared. So that's 3.6 times 10 to the minus 3, or 36 times 10 to the minus 4. So this is going to be 0.0036 meters squared down here. And the units of my top, I see I've got 1 Coulomb canceling. Don't forget those are Coulomb squared there. So I have a Newton per Coulomb left. So what is this? It is 36 over 0.0036. That looks like 10,000 newtons per Coulomb times Q. So when I multiply by this Q in coulombs, I'm going to get just newtons, which is what I know I need to have for that electric force. So next we've got the gravitational force. I can see that T cosine 37 minus mg. What is my mg here? Well, my mass is 0.01 grams, so that's that's 100th of a gram, which means it is how much of a kilogram? Well, I got to move 3 decimal places, so that must be 10 to the minus 5 kilograms times 10 meters per second squared. Sounds to me like 10 to the minus 4 newtons is how much that mass weighs, and that's equal to 0 as well, the difference between those two forces in the vertical direction. So we can figure out first, what is the tension in that string from the first equation here, the x equation. This is in the x direction. Is it? No, that's in the y direction, and this is the one in the x direction here. So I see that T is equal to 10 to the minus 4 over cosine 37. 10 to the minus 4 what? Newtons divided by cosine of 37, and I know that is the angle in a 3, 4, 5 triangle. Which one goes with cosine? Is it 0.6 or 0.8? Well, I know it's 0.8 because that angle is less than 45 degrees. So this must be the number that's bigger than 0.5. So how is this going to work out? Well, bigger than square root 2 over 2. We have 10 to the minus 4 over 4/5, so that's the same as 10 to the minus 4 times 5/4. So that looks like 1.25 times 10 to the minus 4 newtons. Is that a reasonable number? Well, what would the tension be if this were just hanging at rest vertically? I know that it would be the weight of this mass, which we already figured out was 10 to the minus 4 newtons. Does it make sense? It's a little bit increased in order to swing this out at an angle. That makes sense to me, so that sounds like a good solution for the tension. And the last thing we want to know is, how big is that Q? So let's take a look at that. Well, what do we see? Q must equal T sine 37 minus this force is 0. So, bringing this equation down here, T sine 37 is 0.6, must equal the electric force, which we already saw is 10,000 newtons per coulomb times Q. 10,000 newtons per coulomb times Q. So Q must equal 10,000, Q must equal 0.6 times the tension, and what is the tension? 1.25 times 10 to the minus 4. Newtons, divided by 10,000 newtons per coulomb. So I've got newtons over coulombs is going to give me coulombs. And what is this? It is 6/10 times 5/4 times 10 to the minus 4 all over 10 to the 4. 1, 2, 3, 4. So that is looking to me like 5 times 6 is 30 over 10 times 4 is 40. That's going to give me some combination of 7 and 5. 7.5 times 10 to the minus 9 coulombs, or 7.5 nanocoulombs. So that is how we calculate the net force, or the charge on that right pith ball, as well as the tension in the string. I hope that's helpful.